there? Is that one working? Awesome, good, great. Now that we figured out Zoom, perfect. I believe that with generative AI, we're actually at a turning point. The turning point in the way that we will process, analyze, and create visual content. I believe that this will have profound implications on all applications that deal with image and video data, so essentially everything of society and industry. I find it, however, interesting that recently there's been a lot of discussion in industry and research whether the future would be all up to simply scaling those algorithms rather than doing methodological research. And we've seen a lot of interesting applications in LLMs and also in visual models recently in that direction. So let's see where we stand and where we will be going. Some 60 years ago, Richard Feynman, the great physicist and Nobel laureate, gave this talk called "There's Plenty of Room at the Bottom," in which he single-handedly predicted the next 60, 70 years of miniaturization and scaling essentially down that led to nanotechnology and essentially to the revolution that we're having in computing these days. So essentially gave the basis for all of the digital age and beyond. Some years later on, another Richard essentially concluded that the lesson of these 60, 70 years afterwards was essentially that the only thing that you should be doing is simply scaling up your algorithm. That methodological research was not the way to go, or at least not as effective. So essentially saying that breakthrough progress has and will in the future arrive simply by scaling computation and not so much by an approach that actually improves the methodology. So if you would put this in a single meme, it would essentially be that this would be the end of methodological research. Computer vision, like CVPRs as we're doing it here, and the future would belong to Moore's law and essentially just ramping up computation. I guess there's good evidence for that. If you look at several decades of computer evolution, Moore's law kind of panned out nicely, and you see that by reducing transistor size, capacity was reduced. That led to the voltage being reduced and essentially frequency going up. And with that, an enormous increase in terms of computational power. But there was a turning point. Around 2006, which I guess we've all noticed, Dennard scaling came to an end. And frequencies did not increase anymore. The integration process also slowed down. The next thing that people had evidently done was parallelization, but Amdahl's law tells us that we also cannot parallelize at infinitum, that the gains will also be diminishing. And with that comes really the question where to go. Now you might say, like, wait a minute, isn't there something like GPU computing? And that's true. Like the moment that the scaling of CPUs actually stopped, we've seen GPU computing to really kick in. But the issue here is that the demand that we've now seen by means of all the algorithms and the scaling up of algorithms that we've been recently doing is actually over proportional, significantly larger than what we see on the supply side. So the demand outruns the supply by pretty much an order of magnitude. And it seems like it's going to continue exactly that way. And that's why it's a question like whether we can effectively sort of ramp up compute, or whether we would have diminishing returns and eventually a plateauing happening, as we tend to see here. To just make this point here further, over the last 5 years, especially in LLMs, we've seen a 15,000-fold increase in terms of model size, and compute just did not keep up with that and does not seem to keep up with that for reasons that I just outlined. But towards the very right that you see there, you see some recent developments. GPT-4 evidently being an example of model sizes going further up, but with Palm 2 and similar models, and also in the visual domain, something that I'm going to show you now, we see evidence that you don't need to just arbitrarily sort of scale up architectures. Because for every doubling of the size of your models, you essentially would also want to be effective, have a doubling of your data size, data set size, and that amongst many other things causes that to be a problem. Now, there are several laws that we can draw from what we've seen over the past years there. My first one being that architectures that can better exploit commodities that really scale nicely are the ones that will win. That was in computing, evidently, the chip integration. That was in our field what caused the transition from rule-based approaches over to learning-based approaches, because you can only write so much of a program, but learning, observing data and learning from that evidently scales nicely. That was what caused the transition from kernel methods over to CNNs and recently strong likelihood models, because they're better in exploiting large amounts of data and better parallelization. And that was what caused a lot of transition from supervised over to self-supervised approaches, because, hey, unlabeled data scales much better than labeled data. So we see with all these approaches that increasing compute actually, or increasing any of these scalable commodities led to increases in performance. But I believe there are limits to growth. And the first thing that we actually need to notice is that while we see this progress there in the single commodity, of compute, for instance, the story is much more complicated. Compute, for instance, has just been the single most consistent factor over time. But if you really want to look at the story, you need to see that the single factor has overshadowed a lot of much more heterogeneous developments that were necessary. It's not that we took the tubes that we had decades ago and just made them smaller and smaller and smaller. That happened only to a certain factor. Then came a fundamental change in architecture, a paradigm shift over to transistors, which got smaller, then over to integrated circuits, which got smaller. But my point here being like, it was important to have this methodological developments in the meantime, and we had this also in our fields, changing in architectures from SVMs to CNNs and so on, or in training paradigms, as you know. And with that, I believe that we are now seeing calls for a change. We see that even for the richest companies out there, the costs that come by just ramping up compute become staggering. In Palm, several millions of dollars. GPT-4, we don't even know. But more importantly, it means that there will be fewer and fewer players in the field that are actually able to compete that game. And that means essentially we will have less diversity, less clever heads, meaning less creativity out there. But even more importantly, that there will be a monopoly on a crucial technology, a technology which I believe will be crucial for society. Having that in the hands of just a few players is evidently a questionable thing to do. Other things like data privacy and so on, I'm not speaking about that. But if we also need an ever-growing amount of training data, question will be, will that scale up? Training data, getting more and more training data, especially data which is not correlated, is a highly costly process. How about ethics? Annotations being done in the global south, copyright and similar issues. Just scaling up, will that help us in a world where we have long tail distributions? Yeah, IKEA world is great. A few more images and you will get all the Billy shelves done. But what will you do with Da Vinci? Long tail distributions. And the last point being, that's not really intelligence, right? Intelligence, as we know it, typically has to deal with limited, with finite resources. Yeah, learning is not, and we are using the same brains that our ancestors have done when they were dealing with sticks and stones. And I don't have a balcony to my brain or anything. Yeah, the resources are fixed in the skull, and still we have seen enormous power of intelligence and learning adapting to now utilizing machines and the like. So the goal of my group was for quite some time to democratize the research in this field of visual synthesis by essentially rendering smaller models more powerful. How can you make them powerful and at the same time accessible? The first point was evidently releasing them open source, which we did. The second one was right from the bat deciding to make these models fit on consumer hardware for $300, $400. And since these models need to know about pretty much all the world, that means they need to look at billions of training samples, hundreds of terabytes of data, which you essentially need to condense to just a few gigabytes these days. Stable diffusion, which we there developed, fits in your mobile phone. So how can you condense essentially the internet so that it fits in your pocket? I believe that this is a very tricky, challenging feat of intelligence, doing this abstraction, and that's essentially where we went with stable diffusion. So the what you then get is a system where you can simply type in what you would want as an output: sunset, mountain range, oil and canvas, or you change it to a vector image, but something that also caters to a lot of more tasks, such as in-painting, super resolution, or ramping up sketchy renderings. Now, we've been in that field as a community for a while, and we've explored different avenues. And we've seen with that a classical dilemma. A dilemma between models that give us great sample quality, like generative adversarial networks, but which are lacking the coverage of data, prone to mode collapse and so on, or approaches on the other hand, which give us great coverage of the data, but which are lacking quality, like variational autoencoders. It's been really great to see powerful likelihood models come around. Autoregressive models like transformers, more recently diffusion models. Diffusion models for me stick out in that they're score-based, meaning that we finally got rid of the partition function, that we have a stable training objective. So no minimax optimization, which was so tedious task there. And we have Latin variables, which allow us optimization and so on, but they're evidently still costly to train. Now, I guess in this workshop, I don't have to explain how diffusion models work, but I can directly conclude one issue that we've actually observed with likelihood models, such as diffusion models. And that is that the strength of these strong likelihood models is at the same time also becoming kind of a weakness of those, meaning that they try to home in any bit and detail of the likelihood of the data likelihood. So essentially, they concentrate on details that you and I would not want to pay attention to. The differences between the faces that you see there on the right, differences that we would not notice. And they spend comparably little bits on things that actually matter to us. The semantics, the differences between the gender of the person, length of hair, and whatever else it is. So how can we make these models concentrate more on the left, on encoding the semantics, and with that learn what we actually would want to do? The brute force approach would be just increase model size. With that, the entire curve, rate distortion curve, is pushed over to the top right with the evident problems that I mentioned beforehand. The alternative is really have the model focus on the meaningful detail that's out there. And that's what we've done when we developed stable diffusion, going for an architecture such as a UNet there, which tries to map from noise over to the domain, to image data, for instance, but not doing that directly. Rather, learning first a perceptual compression, an approach that goes into a latent domain that compresses the image data in latent domain, and essentially says, like, I don't care about like how each individual hair on the fur of this dog is standing. I just care about the color, the rough length, and the direction, but not what each individual hairs they're doing. And learning then also the decoder to go back. And with that, we have this compression there. And then the powerful likelihood models live in this latent space and can concentrate on what they're really good at, learning long-range interactions. So we see combining the benefit of convolutional architectures with their inductive bias and making them the likelihood models focus on the long-range interaction rather than these local details. With that, you cannot do just text to image, but a lot of different tasks, layout to image, super resolution, and the like. And there's been a lot of work built on stable diffusion in these few months afterwards. Professionals now have access to tools integrated in Photoshop, Blender, After Effects, and so on, and approaches such as ControlNet really ramp up the performance of stable diffusion to quickly tune it to different tasks. But let's look a little bit further. So far, I've shown you how we can take powerful likelihood models and learn representations with these more effectively by essentially concentrating them at what they're good at, learning long-range interactions. But what should we learn at all with such models? I mean, when we look at artists, Monet, when he was painting trees, he was actually looking at trees. He wasn't sitting there in the lab and saying, like, I have seen enough trees. As Ronald Reagan so infamously said, a tree's a tree, right? How many more would an artist like Monet actually look at trees to get this concept of what a tree actually means? But we all know that this makes sense because nature comes with an infinite amount of variability when it comes down to trees. And him watching those serves as an inspiration. And secondly, he evidently does not need to memorize all of those details, in contrast to our humble neural networks. So we are essentially playing this game of stuffing all the training data into these very precious and costly parameters of the neural network. Why do that? Learning is really knowing where something is standing out there, and being able to dig it up. Can't we go for an approach more like Monet? And when we want to paint something, look it up where it is, online, on the fly. And that's a kind of paradigm shift that we try to push forward with this work that we published last in Europe. The question is really if it's a paradigm shift, because others like Alyosha had done this already 20 years ago, essentially utilizing databases and retrieval in there. And the idea is essentially now combining these powerful likelihood models with another approach that makes sure that we're not representing all local details in such a generative model. Instead, we're looking at a database of patch examples. So you're just cropping a lot of patches from the world there, storing them in the database. And as you do visual synthesis, you essentially do lookup in this database. So in our case, that meant like taking 1 million images, 20 million patches that we cropped from this database. And the likelihood model can then concentrate on learning the composition of those patches, but does not need to memorize the content in each individual of those patches. So how does that work? We're looking here at a semi-parametric approach. We take neurosynthesis, and as usual, you take an input image, and you want to reconstruct this image. In between is an autoregressive model or your diffusion model. But rather than directly learning this distribution that you see there towards the left, I guess it should be clear that if we condition this distribution on patches which are meaningful for the synthesis task, life would be easier. So just consider the patches at the bottom. If I want to synthesize this eagle there, having a hold of those patches that you see there next to this eagle, these retrieved patches, these nearest neighbors, should definitely make your synthesis of this eagle easier. And that's exactly what we're doing up there. When you want to synthesize this patch, you essentially then condition on the nearest neighbors, and that simplifies the task of synthesis, not directly the nearest neighbors, but clip encoding of those nearest neighbors. And both this clip encoding as well as this nearest neighbor approach are actually fixed. They're not further adjusted. Inference then means that we're having no access to the training data. We're just utilizing a database that can be different from the training set, and we can even change this during testing. And then we can simply change tasks by swapping the database here, conditioning either on something which is similar or conditioning on a text prompt and finding samples from this database conditioned on this text prompt or similar things. But most importantly, I find that you can actually swap this database post hoc after training. So let's say you train on ImageNet, build a model that can do visual synthesis there on ImageNet. And then you post hoc swap this database for something coming from WikiArt. In that case, the model retrieves patches which are now stylistic patches and essentially does style transfer in a zero-shot manner without ever being trained on that. So you can imagine the potential of an approach like that, where you simply, by swapping a database that you do your retrieval from, without any further training, you can swap tasks and direct the approach in a different direction. Now you may say, wait a minute, like semi-parametric approaches, I know this, right? I mean, they just push things from training in a testing domain, and that must be slower. But not so. Thanks to Google and the scan library, retrieval, approximate nearest neighbor retrieval is super fast. So that goes in 100 milliseconds there, adds no extra cost. And as a matter of fact, we can now make the model size significantly smaller, as you see here. The model size significantly smaller, and that actually leads to a 10-fold increase of computational speed and inference time. So in summary, don't learn the samples and your precious parameters of your autoregressive and diffusion model. Rather have these powerful likelihood models concentrate on what they're good at, learning compositions of the samples. That leads to smaller model sizes, improves their performance, and allows also for a very convenient post hoc transfer of models to novel domains. And with that, I want to switch gears to a last bit that I want to show you, and that's actually answering the question how we can truly understand our world, because I believe that apart from designing tools, which are great for industry and for society and have quite a bit of value there, but I believe that's really what we are also here at, like using vision as a tool to really understand our world. And for that, we need to answer the big questions that every child would answer in that particular situation, the big what if question. What if I would poke a stack of glasses there at the bottom? What would happen? And that's what each little child does, playing with, hopefully not this towers of glass, but with bricks. What would happen if I would poke one of these blocks there? How would nature react? What would happen there? And with that, learn about physics and so on, and the interdependencies of objects and their kinematics. And that's kind of what we've been doing in an approach that we called iPoke and published at ICV a bit ago. Essentially giving you the ability to take a static image and pull on individual pixel in this image, one or several ones, and then make predictions about how the rest of the pixels, the objects in that scene, would actually evolve. Now, it's clear that this is a heavily underdetermined problem. You pulling on an individual pixel, the object might react in different ways. So it's clear we need to sort of adopt a stochastic regimen there and be able to sample from the manifold of our options. A second thing is we want to have this model, this approach be generalizable to new instances of a class and not be specific to a single one. And we want this to actually not rely on an object model or anything. We want to be able to learn this just from the pixel data and not require a physical model like we've here seen very often of individual objects, but simply by watching then a different video, be able to then make predictions about potted plants or whatever else there is. And I had two challenges that we need to solve with that. First is learning the kinematic interdependencies. What happens with this potted plant if you pluck and pull on individual leaf? How are the rest of the pixels reacting? What's the interdependencies between different leaves there? And the second is we want to be able to generalize to novel objects. Now, you're provided with a very sparse control signal, one or several pokes that you have there on individual pixels, and a start frame. And you want on the output side to provide a set of video frames, have a decoder architecture in between. It's clear that no one-to-one correspondence is going to do the trick because it's heavily underdetermined. You simply don't know the kinematic interdependencies between this one pixel that you're provided and or which motion you're provided and the other pixels that are around. So we need to learn these kinematic interdependencies. And for that, we are utilizing a conditional invertible neural network, which essentially learns the kinematic representation, how all the pixels are reacting, and gives us a one-to-one correspondence between this latent representation that we're learning and the video that we actually would want to come and get out, conditioned on this control signal, which the user has provided. If you then put on top of that a video approach, GRU, or whatever else to bind these individual frames together, you can decode that in a video. Training works by taking a video sequence and encoding that into this latent representation. And because this is now a bijective mapping, an invertible neural network, you can take this representation and map it into this latent domain. And so you can take the frames that you've observed and map them over onto the kinematic representation conditioned on the user feedback that you've seen. So you can go either way. During training, you go towards the left. During inference, you then sample something from this kinematic distribution and sample one or several videos. That approach then allows you to simply pull on individual pixels and animate how the object is then moving about. You can take these potted plants here, pull on individual leaves, and then get here towards your right, different renderings of how this object would actually behave, because it's underdetermined. There are different realizations in that particular situation. You can do that for people as well, like pull on the arm and then animate like 4 different ways that the person would have behaved with that sparse signal. And you can, with that, do that over a lot of instances of a class and then get ideas of semantic interdependencies. So what would happen if I would pluck or would push here the head? What would happen if I would push a pixel on the torso of the person? How would other parts of the body actually behave? What are the semantic interdependencies on the spotted plants? Like which leaves are linked together and which ones are not? So with that, let me wrap up. I believe that an approach which purely focuses on scaling will have issues which will grow and grow, because we see the growth of demand significantly outrunning the growth of supply. We will want to have more intelligent approaches towards learning about intelligence. Yeah, the decreasing effectiveness of just scaling up for a research community will actually drive us in a direction where we would want to also embrace more intelligent approaches. We've seen that combining the efficiency of powerful likelihood models with humble convolutional architectures is actually an important direction. And the lesson from that is more powerful models, that's kind of the opposite to just the scaling, just making the models more powerful is probably also not the direction to go, because these models will then get totally filled up by means of details that you should actually not care about. And that's why we want to have this 2-stage approach, which makes sure that the powerful models can focus on what they're actually good at, running long-range interactions. We've seen that approaches such as retrieval augmentation can then lead to much smaller models by essentially focusing powerful likelihood models on what they're really good at, and that's what we should have them at, which is learning compositions of scenes, and allows for a very convenient post hoc transfer to novel domains. And lastly, invertible approaches, for instance, give us a very good handle on learning the kinematic interdependencies and also the ambiguities that we have in that case for object, and helps us to cope with the very sparse user feedback, embraces a stochastic approach, and generalizes to arbitrary objects. With that, let me thank you for your attention. Let me thank my wonderful team that made all of that possible, and I'm happy to answer any questions if you have.
Thanks a lot, Björn. Fantastic talk. Questions from the audience? As long as people think about questions, let me ask maybe 1 or 2. Where is 3D in all of this?
I guess we've seen a lot of 3D by a lot of very precious colleagues. We're also exploring that. We were taking one step at a time, doing also video now very intensively. But I guess we've, over the last couple of months, seen a lot of firsts, and I did not so much value just doing video or just doing 3D for that sake, but going for approaches that, as we've seen here, explore that in a more effective manner, essentially.
Okay, thanks. One more question.
Yeah.
Yeah.
Thank you. As a person like sees a significant image generation like success story, can you make a prediction for the video generation? Like right now, you definitely know the video generation is not that good, but when do you think that will happen?
Happen what?
Like kind of a success story for the image generation.
Yeah.
Repeat that story in the video generation, like short video.
So when will we see the same thing in fold and video as we've seen in static images? I guess, as I just pointed out, I was amazed how quickly people adopted approaches such as stable diffusion in the video domain, and we've seen quite a bit there. The question is just whether we are already happy with the quality that we presently get. There are nice approaches like Gen 1, Gen 2, and so on, which I believe already show some value there. It's just that much of the work that we've seen there are probably computationally so daunting that they haven't fully unfleshed the potential out there in the general public. But I guess we are on the verge of getting there. So my prediction would be fairly soon.
Thank you.
More questions?
Firstly, thank you for the great talk. So I have a more technical question. With respect to the retrieval augmentation, when you swap out the database or the databases that you have, do you need to retrain the decoder with some learning rate or not at all?
So with the retrieval augmentation, we did not train the nearest neighbor lookup and so on. We did not train the encoding that we used for the conditioning, but you then train, and that's advisable, train the rest of the decoding approach that you have there.
And do you train it with the same learning rate, or do you decrease the learning rate so it does not forget what it learned initially?
That's a good question, yeah. We eventually decreased that.
Thank you.
Let's stop here and thank Björn again. And we'll have a short break for 10 minutes and then we'll continue with Andrea.